Hey everyone, let's take a look at a couple of examples. We're continuing our discussion on friction. One of those examples, I want to look at the idea that as I tilt this book, the block will eventually begin to slide. Okay, and that's going to tell me a little bit about the coefficient of friction there. We're going to assume the block is not yet sliding, and so static friction is what we're interested in. And then once it begins to slide, the problem becomes not quite a bit different, but it becomes different. So let's take a look. So here's the block sitting on the book. So there's a force down, mg, that's the gravitational force due to the earth acting on the block. And then there's the normal force, right? That's the normal force due to the book acting on the block. And then there's got to be an upward force, and that's going to be the static frictional force keeping it there. So the static frictional force due to the book acting on the block. And that static frictional force exists here, and here, and here, right? And then finally the static frictional force gives out. It's not strong enough, and the block begins to slide down. But let's just take a look at the scenario here. And I want to do this in such a fashion that I'm going to put my x-axis along the incline and my y-axis perpendicular to the incline, the book, if you will. And so I know that there's an angle between the gravitational force and the y-axis, and that angle is theta. It's the same angle theta. So when I look at the equations, the sum of the forces in the y direction, I get the normal force minus mg cosine theta. And that's all equal to 0 because it's in equilibrium, right? But once it starts sliding, it isn't. But I'm working the problem right up to the point where that takes place. And this is one of the reasons that I put the x and the y-axis the way I did, because then the normal force is purely y, the static frictional force is purely x, and mg has a component in both directions. But if I use a standard xy, then the normal force has components, the frictional force has components, and mg does not, it's purely y. This way I put two of those forces have no components and one of them doesn't. It's mathematically easier to do. All right, so Fn then is equal to mg cosine theta. Now it's very common for problems where the normal force equals the weight, but that really isn't even the majority of the time. So don't get in the idea that the normal force is equal to your weight. Oftentimes that does take place, but not always. All right, so be careful of that. Then when I look at the sum of the forces in the x direction, I get the static frictional force minus mg sine theta. And that's equal to 0, right? And so if we keep in mind from the previous video, we said the static frictional force is less than or equal to mu static times the normal force. And so we're going to go to the point where it's equal to, and so that's when it just begins to start sliding. And so I have mu s times f normal equals mg sine theta, right? When I bring the mg sine theta to the other side, and so mu static equals mg sine theta over the normal force, but the normal force is mg cosine theta. So notice I get the tangent to theta and the weight cancels out. The weight cancels out in this scenario. And so the coefficient doesn't depend on the weight. It just depends on the material. If I did this on this book versus maybe this block right here, I might get different values because the coefficient between the metal and the book and the metal and the wood are not necessarily the same. They might be close, but they're not the same. So there's a real quick example of an object on an incline. Now the other example I want to take a look at is if I'm pulling on this block. Let's take a look at the forces acting on here. We're going to assume again just to the point where I go, right? So it's static until I break this inequality. And so as I look at the forces in this case, I've got the tension up at some angle theta, and then gravitational force is down, normal force is up, and then the static frictional force is back in the negative direction. Now in this scenario, I'm going to go ahead and keep my x and my y in the same direction, right? I'm not sure, hopefully that X and Y were in the video, but maybe they're not. It might be above my image. Okay, so in this scenario, some of the forces in the X, I've got T cosine theta minus F static equals 0. And so T cosine theta equals mu static times the normal force. But the normal force is a lot more difficult to play with in this case because the sum of the forces in the Y, I'm going to get F normal up plus T sine theta up minus mg equals 0. And so the normal force in this scenario equals mg minus T sine theta. And so when I take this over across, I have T cosine theta equals mu static times the normal force. That's mg minus T sine theta. And so solving for the coefficient of friction becomes a lot more complicated here. Oops. Mg minus T sine theta. Becomes a lot more complicated because that tension is going to cause a variation in that normal force. And so oftentimes when you're pulling something, if you lift up a little bit more, you can reduce that normal force and maybe decrease then the frictional force required. But it's a tough balance here because, you know, you're decreasing the normal force, but you're also decreasing the force that's pulling in the X direction. So just a couple of easy examples, simple as far as the diagram and the equations go, but they give us some pretty good information on how to solve frictional problems. All right, there you have it. If you have any questions on those two examples, please leave them in the comments below. Thank you.